In 1967, a trade journal branded it too primitive for serious consideration. Engineers laughed. Procurement boards scored it dead last. The engine had just 48 moving parts in an era that treated part count as proof of intelligence. Every institution that mattered dismissed it as unsophisticated, unworthy, a step backward. Then, one by one, the complex designs they celebrated started breaking down. The simple engine they ridiculed kept running. It outlasted every sophisticated rival built to replace it, and the story of how that happened exposes a blind spot the engineering world still has not fully reckoned with. In the decades after World War II, engineering culture took on a peculiar logic. The more parts an engine had, the more advanced it was believed to be. Procurement boards tasked with choosing engines for everything from naval vessels to public buses used scoring tables that rewarded intricate designs. Each auxiliary system, be it a turbocharger, governor, or electronic control, earned extra points. Manufacturers responded in kind, packing their engines with features that looked impressive on paper and in glossy trade magazine spreads. The result was a self-reinforcing cycle. Engines grew more complicated, and complexity itself became a selling point. Trade publications like Power Plant Engineering and Industrial Diesel Review routinely praised engines that broke records for part count and system integration. A 1967 review of SAE conference abstracts even noted that designers were encouraged to increase component count to meet perceived reliability standards. Marketing materials boasted of multi-stage fuel pumps, variable geometry turbos, and elaborate valve trains. The message was clear. Sophistication meant progress, and progress was measured in moving parts. Behind the scenes, procurement scoring sheets from the U.S. Department of Defense and major utilities listed separate line items for each subsystem. More features meant a higher score, regardless of whether those features translated to real-world reliability. Engineers learned to design for the scoring rubric, not for the field. The result was a marketplace where a simple, rugged engine, one with a low bill of materials, fewer failure points, and easy maintenance, was seen as backward. Simplicity was equated with lack of ambition, even incompetence. This mindset took hold not just in boardrooms, but in the technical press. Editors and reviewers favored engines that could claim novelty, even if that novelty came at the cost of downtime and repair headaches. Part count worship became a quiet rule, shaping which designs earned contracts and which were quietly sidelined. In this environment, an engine that deliberately omitted complexity was not just overlooked, it was actively dismissed as unworthy of serious attention. The culture of complexity set the stage for what would become one of engineering's most stubborn blind spots. When a low part count engine appeared, boasting just 48 moving pieces, it wasn't just doubted, it was ridiculed. Yet the very criteria that doomed it in the eyes of experts would, in time, reveal the industry's confusion between sophistication and true capability. The backlash was not subtle. In March 1967, a trade magazine headline delivered its verdict in block letters: "Too primitive for modern rail." The editorial voice behind the piece did not bother with nuance. It called the new diesel a relic fit for scrapyards and farm tractors, not the backbone of American freight. The article ran in Railway Age, volume 136, and within days, investor calls began to dry up. At least 2 regional procurement boards suspended pilot programs, citing the unacceptable risk of mechanical regression. The scorn did not stop at the headline. Letters to the editor poured in from engineers who likened the engine's sound to a saw blade on a brick wall. One reviewer in mechanical engineering dismissed the design as a step backward from a century of progress, warning that any operator who chose simplicity over sophistication was inviting breakdowns and obsolescence. Funding evaporated almost overnight. A planned demonstration run in St. Louis was canceled when the local transit authority withdrew its support, quoting the magazine's warning about simplistic power plants that sacrifice efficiency for ease of manufacture. Even suppliers hesitated. A Chicago foundry owner reportedly refused a casting order, saying, "We do not want our name on a project the whole industry is laughing at." No one wanted to be associated with a machine so publicly branded as an embarrassment. Behind closed doors, procurement officers quietly blacklisted the engine, and technical committees issued new guidelines that favored multi-stage governors and electronic controls. The message was clear: complexity was the price of admission, and anything less would be ridiculed out of the room. Yet for the small group who kept working on the engine, the sting of that headline lingered. The public contempt was not just an obstacle, it was a warning shot. In an industry that equated part count with progress, daring to be simple came at a real cost. The mockery was on record, and the stakes were now personal. John H. Miller worked in a corner of the shop that most engineers avoided. His workbench, cluttered with hand-drawn diagrams and stained coffee mugs, was a world apart from the drafting rooms where complexity ruled. Miller's notes, still preserved in the margins of blueprints and on the backs of parts catalogs, tell a story of stubborn belief. He wrote in block capitals, "No governor, no auxiliary pump, no unnecessary parts." In another entry dated March 8, 1966, he scrawled a target: 48 parts or fewer, not one more. Miller's sketches show a kind of mechanical minimalism. He circled every component he thought could be eliminated, scribbling alternatives in red pencil. Where the industry demanded a governor, Miller left a blank space. Where others layered on sensors and linkages, he drew a single rod, a single spring. His annotated diagrams, some yellowed with age, reveal a mind intent on stripping away anything that did not serve the core function. "Let the operator be the governor," he wrote once, underlining it twice. The ridicule did not reach this workbench. Here, the question was always the same. Would fewer parts really mean less to go wrong? Or would the engine simply fail in new ways? Miller's diary records moments of doubt, but also flashes of quiet confidence. After a long night spent assembling the prototype, he wrote, "If it runs forever." In the stark light of the workshop, the philosophy was simple. Every part not included was a problem that could never arise. Miller's team, a handful of believers, took pride in the empty spaces on their assembly diagrams. Their conviction set the stage for the first teardown, where the promise of simplicity would have to stand up to real scrutiny. Laid bare on the bench, the engine's anatomy reads more like a lesson in subtraction than a showcase of engineering bravado. The exploded view reveals just 48 components, each one essential, none ornamental. No web of auxiliary pumps, no labyrinth of sensors, no governor clinging to the side. Where rival engines sprawl outward with layer upon layer of control modules and intricate valve trains, this design stands almost stark. The fuel system is a single line, routed directly to the injectors. The lubrication circuit flows through wide, unfussy passages. Where other engines rely on a nest of seals and gaskets, each one a potential leak, this engine uses 30% fewer sealing surfaces than its nearest competitor. The difference is not subtle. Every missing gasket is a failure that never happens. Every absent linkage is a repair that never needs to be made. The control interface is stripped to basics. One throttle, one manual shutoff. No electronic brain, no multi-stage governor, no redundant sensors to chase gremlins through a diagnostic maze. Even the cooling system is pared down, relying on natural convection and a single mechanical fan. The sum effect is a machine where every part can be named, counted, and understood at a glance. In an era that prized sophistication, this engine's simplicity was almost confrontational. Yet the logic is unyielding. Fewer parts, fewer failures. Each omission is deliberate, each empty spot in the diagram, a silent rebuke to the culture of excess. The design does not just promise less to go wrong, it delivers it, one missing part at a time. The real test, though, would come far from the safety of the workbench, where endurance would matter more than elegance. Salt spray, rough weather, and round-the-clock duty, North Sea trawlers offered no mercy to unproven equipment. On October 28, 1981, the Grimsby Fishing Cooperative placed an order for 3 simple engines, each rated at 300 kilowatts. The procurement memo, filed as GTST-81, reads almost clinical. For immediate deployment, North Sea, winter season. Yet between the lines, it is clear this was a gamble. The ship's chief engineer, Arthur Miller, logged the first hours in a battered maintenance book. His handwriting is steady, his comments spare. Installed on November 14th, ran up to load. Idle smooth. No auxiliary pump. The North Sea's reputation as a proving ground was well earned. Salt crusted every surface. And engines that survived a summer often failed by spring. Over the next 18 months, Miller's log tells the story in numbers. Hours accumulated, 2,000, then 4,800. On June 3, 1983, he noted a nozzle clogging incident. Zero downtime, he wrote. Engine operating within 2% of design, RPM. No teardown, no emergency call to port. The only interruptions were for oil changes and the occasional filter swap. Compared to the maintenance logs of the old multi-stage diesel, pages thick with breakdowns and parts orders, the new engine's record is almost empty. A memo circulated in Grimsby that summer, quietly at first, then with growing confidence. Simple engine, no governor, no auxiliary pump, no failures. Word spread along the docks. Crews from neighboring vessels came to see the engine that kept running while others waited on spares. The maintenance burden, once measured in hours lost to repairs, shrank to routine checks and a single line entry, still running. By the end of the second season, the skepticism that greeted the engine's arrival had faded into a kind of grudging respect. The evidence was there, stamped in the logbook and echoed in every uneventful crossing. Durability was not a claim. It was a fact, written in salt and steel. At the Cedar Rapids Cooperative Elevator, the machinery room was never silent. Conveyor belts rattled, augers churned, and the hum of backup generators was as familiar as the grain dust in the air. Yet, in the mid-1980s, a new kind of noise began to dominate, the clatter of breakdowns. Complex engines loaded with governors and auxiliary pumps became notorious for their sudden failures. Every added subsystem meant to guarantee precision brought another point of weakness. On March 15, 1985, a memo from the County Grain Elevator Board landed on the manager's desk. It was blunt. Governor failures were logged in both main generator sets. Downtime exceeded budgeted limits for the third consecutive quarter. Attached was a failure log. Page after page of stoppages traced back to the same culprits, sticking governors, sensor faults, and cascading shutdowns. Each incident meant lost time, spoiled grain, and mounting repair bills. The maintenance crew, once proud of their technical prowess, now spent more hours diagnosing electronics than moving product. The numbers told their own story. In the previous 12 months, the main generator had failed 7 times due to governor malfunctions alone. Each repair required specialized parts, overnight shipping, and a technician who understood the labyrinth of linkages and control modules. The cost of complexity was no longer theoretical. It was measured in grain lost and overtime paid. For the elevator manager, the promise of advanced engines had turned into a running battle against the very sophistication that was supposed to guarantee uptime. The logbook became a record of frustration, a silent argument against the wisdom of the scoring tables that had pushed for more features, not fewer. As the failures mounted, the idea of a simpler engine, once dismissed as naive, began to look less like a risk and more like relief. In 1992, the Scottish island ferry MV Islay underwent a retrofit that would quietly challenge decades of engineering dogma. The operations chief, facing mounting repair bills from the previous high-spec engine, signed off on a replacement that many still called a gamble, a low part count diesel stripped of every non-essential system. That decision was recorded in the ship's registry, a line item that seemed almost an afterthought compared to the thick files on complex rivals. But as the Islay returned to daily service, something unexpected happened. The maintenance logs, once dense with notations about sensor faults and governor failures, began to thin out. Weeks passed without incident, then months. The ferry's chief engineer, known for his blunt assessments, wrote simply, "No faults. Routine checks only." Across the globe, a government procurement board in Western Australia issued tender DCC 93 SP001. The language was unambiguous. Supply of 150 kilowatt gensets for remote telecom stations, with reliability and ease of maintenance specified in bold. For the first time, a public sector contract favored the simple engine's virtues over the allure of complex features. The tender did not reward the longest list of auxiliary systems or the latest digital controls. Instead, it demanded proof of uptime and the ability for local crews to service the units with basic tools. When the winning bid listed fewer than 50 moving parts, the old scoring tables were quietly set aside. Within 2 years, the MV Islay's service record became a reference point. Other fleet managers and procurement officers began to ask for maintenance histories, not marketing brochures. The simple engine, once dismissed as a relic, was now cited in official documents as a benchmark for reliability. The shift was not announced with fanfare, but it was unmistakable, a silent reversal in what counted as good engineering. Numbers have a way of cutting through opinion, and in this case, the data left no room for doubt. When independent engineering labs completed their teardown of the simple engine, the results were almost embarrassing for its critics. The mean time between failures, MTBF, clocked in at 12,300 hours. The nearest complex rival managed only 9,800. Repair time told a similar story. Average downtime per incident was 3.2 hours for the simple engine, compared to 7.5 hours for the competition. These were not just marginal gains. They were the kind of gaps that forced procurement officers to rewrite their cost models from scratch. Warranty records from the U.S. Navy auxiliary fleet showed a drop in claims from 14% to just 3% after switching to the low part count design. Economists in the Department of Defense, usually buried in spreadsheets, started circulating memos that translated reliability into hard dollars. One memo, dated June 1996, put it plainly. Lifecycle cost per operating hour is less than half that of the previous standard. Spare parts inventories shrank, technician overtime evaporated, and the procurement boards that once demanded complexity now found themselves defending the old scoring tables. These figures did not just win arguments, they shifted budgets. The simple engine's reliability was not a theoretical advantage. It was a line item on balance sheets, a pattern that repeated across marine, industrial, and public sector fleets. Where critics once saw a lack of ambition, the numbers revealed a new definition of progress, one measured in uptime, not ornament. The evidence was unignorable. Simplicity, once dismissed as a flaw, had become the most valuable asset in the room. Today, industries still chase innovation through complexity, often at the cost of reliability. As maintenance budgets swell and downtime cripples fleets, the lesson endures. True progress is measured by outlasting rivals, not by dazzling experts. Simplicity's quiet triumph stands as a warning. Assumptions built on prestige or fashion unravel, while time rewards what simply works. Sometimes the overlooked design is the future everyone needs to rediscover. Share your thoughts below.